Out of all the forces that weave the universe together, gravity seems like an afterthought. If the universe were a concert hall of interactions, gravity would appear as the quietest instrument in the back row. The strong nuclear interaction can bind atomic nuclei with unimaginable intensity. The electromagnetic interaction holds atoms and molecules together and lights the cosmos with the glow of starlight. Even the weak interaction, which governs certain forms of radioactive decay, has more strength on tiny scales. If we were to compare their strengths in ordinary scientific notation, the strong nuclear interaction would stand at the peak, while gravity would cower at the bottom, weaker by a factor so large that it strains imagination. But here, every number must be spoken. The difference in strength between gravity and electromagnetism is roughly 10 to the power of 40. That is a 1 followed by 40 zeros. Such a number does not feel like something a human mind should be comfortable holding. Yet it is gravity that shapes the fates of stars, gravity that sculpts galaxies, gravity that guides the expansion of the cosmos itself. How can a force that is so weak control structures of such impossible scale? The answer begins with a simple truth. Every form of mass and every form of energy feels gravity. A proton does, a planet does, a beam of light does, a galaxy cluster containing trillions of stars does. Gravity never switches off. It never shields itself. It never cancels. It accumulates relentlessly. Imagine the surface of our planet. Humans feel the familiar downward pull that keeps feet pressed to the ground. We rarely question that feeling. But the force that holds us here is astonishingly weak. If you pick up a paperclip using a small refrigerator magnet, the magnet defeats the entire gravitational pull of the planet Earth on that paperclip. Electromagnetism in that simple moment overpowers gravity, not just from a stone or a building, but from an entire world. That demonstration reveals a secret. Gravity is weak, yet patient. It never gives up. Across the universe, matter gathers. Nebulas collapse into stars. Stars collapse into black holes. Black holes gather into galactic cores. Galactic clusters grow into the cosmic web. Each step along this chain of structure is driven by gravity, patiently pulling mass toward mass and energy toward curvature. The universe looks organized and gigantic only because gravity has had billions upon billions of years to work. If we could zoom out far beyond our solar system, beyond the Milky Way galaxy, past the scattered dust of the intergalactic medium, and keep going until the largest cosmic structures become visible, we would see a filigree of light stretching across an invisible scaffolding. Galaxies are not scattered randomly. They form strands tens of millions of light years long. These strands weave together like a web. Every place where strands meet, clusters of galaxies are born. And at the heart of almost every one of these clusters lies a supermassive black hole formed through the inescapable pressure of gravity. This brings forth a paradox. If gravity is the weakest interaction, why does it have the greatest influence over the shape of the universe? First, gravity is the only interaction that acts on everything with mass or energy. Light itself, though without mass, carries energy, and therefore follows the bending of space caused by gravity. Second, although the other forces dominate at tiny scales, their effects fade as distance increases. Electromagnetism cancels out because matter contains equal amounts of positive and negative charge. The nuclear forces vanish at distances even smaller than atoms. Only gravity stretches its influence across cosmic distances. There is no distance at which gravity becomes zero. It only becomes weaker, fading slowly but never ending. Consider how strange that really is. The strong interaction operates inside nuclei. Electromagnetism governs atoms, but gravity commands planets, stars, and galaxies. It is almost as if the universe gives each force its own domain. Gravity rules the cosmos because the cosmos is enormous. The weakness of gravity has another consequence. Because gravity pulls so gently, celestial bodies must gather astonishing amounts of mass to make its effects dramatic. A black hole is not born just because matter collapses. It is born because matter collapses fast enough and with enough density that gravity no longer has competition. A star 100 times more massive than our Sun can collapse on itself when the nuclear furnace in its core runs out of fuel. As the nuclear reactions shut off, nothing pushes outward anymore. Gravity, patient and relentless, wins. But this chapter will not stop at stars. It will not stop at black holes. The central question of this book digs deeper. If gravity seems to grow stronger and stronger as matter collapses into smaller and denser volumes, does that growth go on forever? Could there be a point at which gravity reaches a maximum strength? Would there come a moment where the universe whispers enough? The thought is unsettling. If gravity has no maximum strength, then black holes truly hide infinities at their centers. Infinite density, infinite curvature, infinite warping of space and of time. Physics does not like infinities. Whenever an equation produces an infinite value, it is not describing reality, it is announcing failure. Our understanding has reached a cliff. The mystery becomes clearer when we observe what Einstein revealed. Gravity is not a pulling force. Instead, mass and energy bend the shape of space. Objects move as if they are falling along the curves of that bending. When you drop a ball, gravity does not pull it down. Space itself is curving downward beneath it. From planets to galaxies, everything simply follows the most natural path through that curved space. The more mass gathered in one region, the deeper the curvature becomes. But what happens when the curvature becomes extreme? If the surface of space deepens without limit, the idea of space as a smooth continuum starts to dissolve. At the smallest possible scale, far smaller than atoms, far smaller than protons, a deeper framework of reality must appear. We do not see this hidden layer in daily life. But near the core of a black hole, or at the beginning of the universe, the scales are so minuscule that space-time may no longer behave like a smooth surface. Instead, it might tremble with quantum storms, like a restless ocean made of probability. We are confronted with a boundary. Gravity governs the largest cosmic structures, yet its true nature may be written in the physics of the smallest possible lengths and times. If gravity seems limitless, if it can grow without bound, then the universe becomes a place without a flaw. If gravity hits a wall, a maximum strength beyond which it cannot grow, then that wall is where new laws appear. Somewhere between the collapse of stars and the birth of the universe, gravity reveals a secret. It appears limitless, yet it might not be. Gravity grows silently. It gathers everything. A drifting grain of dust in an interstellar cloud cannot resist. A planet cannot resist. Even light, which feels no weight, bends its path when gravity shapes the geometry of space. The more matter that collapses, the more space curves, and the more space curves, the more matter falls inward. It is a feedback loop on a cosmic scale. Astronomers can trace this process across billions of years of cosmic history. In the early universe, matter was distributed almost evenly. Tiny fluctuations in density began to grow. Gravity amplified these uneven spots, just a little denser here and a little lighter there. What began as a slight preference became a runaway effect. Dense patches became denser still. The result was a universe that eventually developed structure. Stars formed, galaxies formed, then galaxies influenced other galaxies. All because gravity kept adding, never subtracting. We tend to picture gravity as something that pulls downward. We feel our bodies pressed against the ground and assume that this is its true form. But that sensation is misleading. If gravity truly pulled downward, there would have to be a force acting on us all the time. Instead, what we experience is the ground pushing upward to keep us from falling along the natural path that curved space requires. If the ground disappeared beneath us, we would fall not because gravity pulls, but because the curvature of space creates a natural path that guides our motion. Free fall is weightlessness. Astronauts orbiting our planet are constantly falling, never hitting the ground. They feel no weight at all. Now imagine that feeling extending across the universe. Every planet, every moon, every comet is falling. Not downward, but inward along the curved geometry carved by mass. If gravity ended abruptly, planets would not freeze in place. They would shoot off into the cold dark, tracing straight paths forever. Gravity keeps them falling along circles. Without it, every orbit would unspool. When people hear that gravity is the weakest force, they often feel surprise. If it is so weak, how does it bend the path of light from distant galaxies? How does it trap photons forever inside a black hole? The secret lies in how gravity ignores everything except mass and energy. It does not know about charge. It does not know about the difference between protons and electrons. It does not care about the quantum fields that govern the other interactions. Gravity does not see details. It sees only the total amount of mass and energy, and reacts by shaping the stage on which everything plays out. That makes gravity universal. The electromagnetic interaction only affects particles carrying electric charge. The nuclear interactions only affect particles inside atomic nuclei. But gravity affects everything. It does not weaken because of positive and negative cancellation. There is no opposite form of mass that creates a neutral balance. Gravity only accumulates. This universal power is why the cosmos is not a chaotic swarm of particles drifting apart. If electromagnetism were the dominant large-scale force, galaxies would tear themselves apart because like charges repel. If the nuclear forces somehow extended over huge distances, the universe would collapse into tightly packed chunks of matter far smaller than stars. Gravity makes the universe smooth at enormous scales, but allows dense structures to form within it. It offers restraint, not violence. The weakness of gravity also protects us. If gravity were only a little stronger, stars like our sun might burn through their fuel too quickly. Instead of surviving for on the order of 10 billion years, a typical star might last only a few 100 million years. Life as we know it could never evolve. If gravity were significantly weaker, matter might never clump into stars at all. Hydrogen would remain diffuse, drifting through space like eternal fog. The universe would be dark and cold. So gravity is not just weak, it is exquisitely tuned. Its strength defines the possibility of long-lived stars and planets. We owe our existence to the fact that gravity whispers instead of shouts. Yet the weakness of gravity only tells half the story. Inside a collapsing star, gravity reveals another face. When a massive star exhausts its fuel, it can no longer support itself. Nuclear fusion stops, heat fades, pressure falls. The immense weight of the outer layers collapses inward. The atoms inside the core are crushed. Electrons slam into protons. Neutrons form. The core shrinks to a sphere roughly the size of a city. At that moment, the collapse halts. A neutron star is born. A neutron star is gravity at nearly full volume. Imagine a sphere with the mass of our sun compressed into a radius of about 10 kilometers. A single teaspoon of its matter would weigh as much as a mountain on Earth. Gravity becomes so strong at the surface of a neutron star that if you stood on it, even for a fraction of a second, the tidal forces would stretch you into a thread of atoms. Yet even here, gravity has not reached its final limit. Above the mass of a neutron star, gravity wins again. No known form of pressure can resist it. The collapse continues. Nothing can stop it, not even the existence of neutrons themselves. According to classical general relativity, the collapsing matter shrinks to an infinitely small point. Space curves infinitely. Density becomes infinite. This place is called a singularity. Here is the core mystery that drives this book. Infinite density is not a real physical state. It is a sign that our equations have reached their limits. General relativity is magnificent, but it cannot describe the universe when matter shrinks to scales smaller than any particle. At that depth, quantum behavior must emerge. Quantum rules do not permit infinite compression. Something must prevent gravity from increasing without limit. Picture gravity as a steepening cliff. The more matter falls inward, the sharper the cliff becomes. General relativity describes that cliff perfectly until the moment the slope becomes vertical. After that, the mathematics breaks. Not because nature breaks, but because we are using the wrong language. We have reached the question that few dare to confront. If gravity is a curvature of space, and if that curvature deepens with more and more collapsing matter, does the curvature continue forever? Or is there a maximum depth? A moment where space-time refuses to curve further. No one has seen the inside of a black hole. We can observe the event horizon. We can measure the mass, the spin, and sometimes the magnetic field near the boundary. But what lies beyond is hidden. It is sealed off by the strength of gravity. Even information cannot climb back out. There is an ancient idea in physics. Whenever an equation reaches infinity, reality is trying to tell us to look deeper. Gravity may appear endless. It may appear to grow without limit. But appearances deceive. A limit may exist, a threshold, a point beyond which gravity cannot grow stronger. Right now we stand before the cliff. In the next chapter we will step toward the edge and look into the mathematics of curved space-time itself. Space looks empty. It feels empty. When we stand beneath the night sky, looking upward into the dark sea of stars, it appears as though the universe is built from objects suspended in a nothingness that stretches forever. That illusion was so powerful that for most of human history, even the greatest thinkers treated space as a silent backdrop, an unmoving theater in which planets and stars performed their motions. Then came Albert Einstein. Einstein did something audacious. He questioned the stage itself. He asked whether space and time might not be rigid or passive, but active and alive. He imagined space as something that could be shaped and stretched. He envisioned time as something that could speed up or slow down, depending on where you stand and how fast you move. In his hands, the universe became flexible. It bent and curved. In the early 20th century, Einstein rewrote the laws of gravity not as a pulling force, but as the geometry of space and time. The mathematics of his theory revealed something astonishing. Mass and energy tells space-time how to curve, and curved space-time tells matter how to move. Gravity is not a pull. It is a path. The motion we call gravity is nothing more than matter following the curves of space. Imagine placing a heavy sphere on a stretched rubber sheet. The sheet bends and dips under the weight. If a smaller ball travels across the surface, its path deflects as it moves around the dip. The smaller ball is not being pulled toward the larger one by a string or a magnet. It simply takes the most natural path along the curved surface. In the same way, Earth is not held in orbit by an invisible pulling force. Earth is falling continuously through the curved geometry that the sun creates in space-time. Earth is forever falling around the sun and never reaching it. The beauty of general relativity is not found only in its equations, though they are among the most elegant ever written. It is found in the idea at its core. Space is not a void. Time is not a rhythm that ticks the same way everywhere. The universe is a shape. When matter gathers, the shape bends. When matter moves, it sends vibrations of curvature through space. These vibrations are known as gravitational waves. In the year 2015, scientists confirmed the existence of these waves directly with a detection that shook both space-time and our understanding of it. A ripple that Einstein had predicted 100 years earlier washed through Earth, stretching and squeezing space by less than the width of an atomic nucleus. But the most important insight is simpler. Gravity is geometry. Einstein developed this idea from the thought that falling feels like floating. If you are in an elevator that is in free fall, everything around you becomes weightless. A dropped object hovers beside you. In that moment, gravity disappears. You and the object both follow the natural curve of space. Nothing forces anything. The path is effortless. This realization led Einstein to one of the most profound connections in physics. Free fall is the most natural state of motion. When something feels heavy, it is not because gravity pushes down. It is because something prevents us from falling. Our weight is not the force of gravity pulling us down. It is the ground pushing us up. Once we accept that gravity is not a force but a curvature, an entire universe of new questions opens. How deep can curvature become? Can space-time fold so tightly that it tunnels into itself? Can curvature become infinite at the center of a black hole, or does something stop it? Under ordinary circumstances, space-time curves gently. Earth curves space only slightly. The sun curves space more strongly. Even a massive galaxy curves space, but only subtly on human scales. We cannot notice it as we walk or drive or look around. It takes precise instruments to detect that time passes slightly slower at sea level than on a mountain. The difference is measured in mere fractions of a trillionth of a second, yet the effect is real and measurable. Time itself is influenced by gravity. Now imagine increasing the density and the mass. A collapsing star squeezes more and more matter into a smaller and smaller region. The curvature grows steeper. Space-time becomes like a deep funnel. At the bottom of that funnel, the mathematics of general relativity predict a frightening result. As density approaches infinity, space-time curvature does as well. The funnel has no bottom. It simply drops off into an infinite pit known as a singularity. A singularity is not a physical object. It is the mathematical equivalent of a warning sign. It says our equations no longer describe reality. Infinity is a signal that we have reached the boundary of a theory. Einstein did not want singularities. He believed the universe must have a deeper logic, but his theory led to them anyway. When a massive star collapses, space-time curves until nothing can escape. The event horizon forms. Light itself is trapped. From that moment, the collapse continues until the equations yield infinity. But the universe has taught us a lesson again and again. Whenever physics predicts an infinity, something new waits beyond it. Einstein gave us a picture of gravity as the bending of space-time. But he did not tell us how space-time behaves when the bending becomes extreme. His theory works on planetary scales and galactic scales. It even works on the edges of black holes. But in the heart of a black hole, or in the first fraction of the first second after the birth of the universe, his theory breaks apart. A new framework must take over. To find that framework, we must go smaller. We must travel into the realm of the quantum. The smooth surface of space-time that Einstein imagined might not be smooth at all. Zoom in far enough, and space-time may become grainy like the pixels on a screen, or like the threads of a fabric. With enough magnification, the soft curvature Einstein described could reveal something turbulent and chaotic. Something ruled by probability, not by flawless geometry. Gravity dominates at the largest scales. Quantum rules dominate at the smallest. Somewhere between them lies the true nature of the universe. When we shrink our view smaller and smaller, another universe begins to emerge. Inside that universe, the certainty of classical physics dissolves. Particles flicker in and out of existence. Position becomes a suggestion rather than a fact. Time loses its steady beat. At this scale, the rules that guide planets and galaxies fall silent. Quantum mechanics takes over, and its language is unfamiliar to our everyday sense of cause and effect. The world becomes a haze of possibilities. Events have no definite outcome until something observes them. Einstein was never fully comfortable with this strange realm. He once said that the moon is still there, even when no one is looking. Quantum mechanics quietly answered that reality may not be so simple. But even though Einstein resisted the deepest philosophical consequences of quantum theory, he loved mathematical beauty. And he knew that his theory of curved spacetime left questions unsolved. He suspected that there must be a deeper unity connecting gravity to the quantum world. To understand why his theory reaches a breaking point, imagine spacetime as a smooth fabric. In ordinary conditions, that fabric curves gently. But when enormous mass is compressed into a small region, the curvature increases dramatically. In the mathematics of general relativity, there is nothing to prevent the curvature from growing forever. As the collapse continues, the radius shrinks, the density increases without limit, and the curvature becomes infinite. But infinity is not a physical result of nature. It is an error code produced by our equations. Deep inside a black hole, matter falls toward the center, but the closer matter gets to that center, the smaller the region becomes. Eventually, the scale shrinks to the point where the smallest unit of measurement in quantum theory becomes relevant. There exists a fundamental scale known as the Planck length. It is unimaginably small, on the order of 10 to the power of negative 35 meters. We cannot write it as a decimal without pages of zeros. If an atom were expanded to the size of Earth, the Planck length would still be smaller than a single grain of dust on that planet-sized atom. This is the frontier where space-time may stop being smooth. At scales this small, quantum fluctuations become violent. Virtual particles appear and vanish. Energy spikes and collapses again. The very idea of a smooth geometry loses meaning. It is as if reality is built from discrete quanta of space-time, small indivisible chunks that cannot be subdivided. Many physicists suspect that space-time may be woven from something like a network of tiny loops or threads. If this is true, then gravity cannot increase without limit. The curvature cannot deepen forever. There would be a maximum allowable curvature, a maximum density, and beyond it, the collapse would be stopped by the quantum structure of space-time itself. Einstein gave us the large-scale shape of the universe. Quantum mechanics gave us the language for the small scale. But these two descriptions do not yet merge into a single picture. They do not hate each other, but they do not speak a common language. General relativity describes a smooth world of continuous geometry. Quantum mechanics describes a granular world of probabilities. If we try to combine both theories using the mathematics we currently have, the result is chaos. We are left with nonsense equations full of infinities. The universe refuses to be understood through half-finished explanations. Consider again the collapsing star. General relativity says the matter will continue collapsing until it forms a singularity. Quantum mechanics says that nothing can be compressed into a region smaller than the quantum of spacetime. These statements cannot both be correct. Somewhere between them lies the truth. Physicists call this conflict the problem of quantum gravity. It is not simply about adjusting numbers or constants. It is about rewriting our understanding of reality. If gravity is the shape of space-time, and the quantum world changes the nature of space-time at small distances, then gravity itself might be an emergent phenomenon. It could arise from something deeper, something more fundamental than the fabric of space-time. The search for this deeper theory has given rise to ideas that sound almost mythic. Some researchers imagine tiny, vibrating strings that generate all particles. Others imagine that space-time is made from a collection of discrete loops of geometry, each loop representing a quantum of volume. Some imagine that gravity is not fundamental at all, but an illusion emerging from information itself, just as temperature arises from the motion of atoms. Each of these possibilities attempts to bridge the gap between the continuous and the discrete. To fully appreciate what is at stake, imagine two views of the universe. The first view is the Einstein view, smooth and continuous. Space-time curves elegantly. The second view is the quantum view, jittery and granular. If you zoom in far enough, the serene curves of general relativity may reveal themselves as the collective behavior of countless microscopic elements. Just as a painting appears smooth from afar yet is made of tiny strokes when seen up close, space-time might be built from quantum pieces. If that is true, then gravity has limits. Every fabric can stretch only to a certain point before its threads resist further deformation. Every field has a saturation point where further intensity stops producing additional effect. Every physical quantity has boundaries, so the question becomes unavoidable. What happens when space-time approaches that boundary? If a collapsing star reaches the point where space-time refuses to compress further, something must occur. Perhaps the collapse rebounds. Perhaps a new pocket of space-time forms. Perhaps the black hole contains a core that stores information like a vault at the bottom of a deep gravitational well. General relativity predicts inevitability. Quantum mechanics predicts uncertainty. A complete theory of quantum gravity would predict what actually happens. It would answer whether gravity has a maximum strength. We are not at that revelation yet, but we are close enough to see the shape of it in the distance. The search for that answer will lead us to the concept of the Planck scale. It will lead to ideas like string theory and loop quantum gravity. It will lead to a new kind of star, one that exists only in theory, born from the moment when collapse cannot continue. And eventually, it will lead us to the center of a black hole, where reality bends into mystery. Gravity begins as gentle curvature. It ends as a question. There is a place in physics where every known theory fails. It is not a physical location like the center of a black hole or the beginning of the universe, although those places force us to confront it. This frontier is a scale of size and energy so extreme that the familiar language of space and time begins to stutter. It is known as the Planck scale, named for the physicist Max Planck, who first discovered that energy might come in tiny packets long before quantum mechanics was fully understood. To understand the Planck scale, imagine shrinking your point of view smaller and smaller. A mountain becomes a grain of sand. A grain becomes a molecule. The molecule becomes an atom. The atom becomes a proton or a neutron. Inside that proton or neutron are smaller particles known as quarks. Keep shrinking. At this point, we reach the smallest distances ever probed by particle accelerators on Earth. But we are still far from the end. Continue shrinking until the very notion of space begins to tremble. We approach the Planck length. This distance is roughly 10 to the power of negative 35 meters. All the zeros necessary to write that number would stretch across a page. The Planck scale is not just small. It represents a limit on how fine our measurements can be. In everyday life, we can cut lengths in half again and again. At the atomic scale, we can still divide space mentally, even if our tools cannot follow. But the Planck length suggests that space-time may not be infinitely divisible. It might have a lowest possible unit, just as digital screens have pixels that limit their resolution. If space-time has something like pixels, then gravity cannot curve space beyond a certain point. It would reach the boundary of the smallest unit. Along with the Planck length comes the Planck force. This represents the largest force that space-time itself can sustain. Physicists estimate it to be on the order of 10 to the power of 44 newtons. For comparison, the gravitational pull between Earth and the Sun, enormous by human standards, is tiny next to that number. It is like comparing the gentle brush of a feather with the impact of a collapsing star. But what does it mean to say that a force is too large for space-time to handle? Imagine the rubber sheet analogy again. Place a heavy sphere on the sheet and it sinks into a smooth curve. Add more weight and the dip becomes deeper. Now imagine pressing so hard that the sheet is forced into a point where its surface would have to fold, infinitely sharp. The fabric cannot do it. Instead, it tears. In the universe, space-time cannot tear, so something else must happen. The equations of general relativity try to force the curvature to grow without limit. Quantum mechanics stops it. At the Planck scale, the smooth surface that Einstein described is replaced with something wild. Space-time does not behave like a calm sea, but like a storm of foaming probabilities. Physicists sometimes describe it as space-time foam, but that phrase is only an approximation. What truly happens there is beyond our visual metaphors. Distances and durations lose their meaning. The familiar link between cause and effect becomes clouded. The deep structure of space-time reveals itself not as a fabric, but as a network of tiny interactions. Why do we believe such a scale exists? Because if we combine the three deepest constants of nature, we arrive at the Planck units. These constants are the speed of light, the gravitational constant, and the quantum constant, discovered by Planck himself. When combined mathematically, they produce units of length, time, and energy that seem to mark the limits of what can physically exist. It is not arbitrary. It is as though nature encoded a boundary into the numbers that shape our universe. At the Planck scale, quantum fluctuations of energy become so intense that tiny black holes might pop in and out of existence. Space curves abruptly and then uncurves. Time flickers. Everything that seems stable at human scales becomes uncertain and fragile. No object can remain still. No location can remain precise. Even the idea of before and after begins to blur. For gravity, this is a crisis and an opportunity. General relativity allows gravity to become arbitrarily strong. But at the Planck scale, quantum mechanics says no further. Space-time cannot continue to curve without limit. If too much mass or energy concentrates into too small a space, the curvature would demand infinite density. The mathematics of general relativity try to continue, but quantum rules intervene. They say that space-time has a smallest grain. That grain resists further compression. In other words, gravity might have a maximum strength, a point where it cannot grow stronger, because space-time itself refuses to bend further. Somewhere between quantum randomness and the elegant curvature Einstein described lies an undiscovered truth, a theory that merges the continuous world and the granular world. The Planck scale is not just a boundary of measurement, it is a boundary of meaning. If gravity approaches its maximum at the Planck force, then our understanding of black holes must change. Instead of collapsing to infinite density, the matter may reach a state so compressed that further collapse becomes impossible. Something must happen next, something surprising, something new. The Planck scale is where the universe guards its deepest secrets. At the Planck scale, the universe becomes unrecognizable. Our minds are trained to believe that space is empty and smooth, and that time flows in one direction, steady and dependable. But within this unimaginably tiny domain, that comforting image dissolves. If we could somehow shrink ourselves in thought to that scale, we would discover that nothing behaves in a familiar way. The smallest possible regions of space-time erupt with activity. Energy bursts into brief existence, then vanishes. Space does not remain flat. It ripples and folds into microscopic pockets. Time jitters. The void is alive. Physicists sometimes speak of this realm as the quantum foam. The term may sound whimsical, but behind it is a profound statement. Foam exists when bubbles form and collapse so rapidly that we cannot track the boundary of each one. The Planck scale may behave in a similar way. Tiny bubbles of space-time appear and collapse almost instantly. They are not bubbles of gas. They are bubbles of geometry. Within those bubbles, gravity may fluctuate so wildly that miniature black holes form for a brief and insignificant fraction of a second, then evaporate instantly. To understand why these fluctuations become so intense, we must consider how gravity responds to energy. In general relativity, energy and mass are the same. Compress enough energy into a small enough region, and gravity grows stronger. Compress still more, and gravity grows yet stronger. But quantum mechanics tells us that energy in a tiny region is uncertain. It cannot be pinned down with exact precision. The smaller the region we try to examine, the larger the uncertainty becomes. At the Planck scale, that uncertainty becomes enormous. Energy spikes so high that gravity should, according to general relativity, create a tiny black hole. But that black hole evaporates almost instantly because of quantum effects. Space-time is not calm, it is frantic. At human scales, we do not perceive this frenzy. We see calmness. We build bridges and skyscrapers and compasses and telescopes because we believe in the stability of space and time. We use clocks to measure hours and days. We use rulers to mark distance. Everything seems continuous. Everything seems reliable. But the deeper physics suggests that space-time may be a complex network of discrete elements. We do not know what those elements are. They might be loops of geometry. They might be vibrating strings of energy. They might be something even more abstract that we cannot yet imagine. The truth remains hidden behind a veil that human intuition has never had to pierce. We also suspect that there is a maximum intensity of gravity. At everyday scales, gravity seems gentle. At the surface of Earth, we feel only a mild downward pressure. In orbit, astronauts feel none at all. Near a neutron star, gravity grows fierce. Near a black hole, it becomes terrifying. The curvature of space-time near the event horizon becomes so steep that light cannot escape. But inside that horizon, the equations of general relativity demand more. The collapse continues. The curvature deepens. The density grows without limit. And at the very center, the mathematics calls for infinity. Physicists do not believe that infinity exists in nature. Infinity is a signpost that says our understanding is incomplete. Somewhere between the event horizon and the imagined singularity, quantum rules take command. If space-time is made of discrete quanta, then space-time cannot be compressed into a volume smaller than that quantum. Compression reaches a limit. Gravity reaches a limit. The Planck force is that limit. Imagine a bowstring stretched tighter and tighter. As the tension increases, the string resists more strongly. Eventually, there is a point where no further stretching is possible. If you try to tighten the string beyond that point, something must give. In the universe, the space-time fabric itself may behave in a similar way. The Planck force is like the ultimate tension the universe can endure. There is an astonishing consequence of this. If space-time has a smallest unit, then the interior of a black hole cannot collapse to a point of infinite density. Instead, something must stop the collapse. matter reaches a state of maximum compression. Gravity reaches its ceiling. Beyond that point, the laws of general relativity are no longer valid. Quantum gravity must take control. This threshold is like the boundary between two worlds. On one side lies the smooth geometry described by Einstein. On the other lies the quantum landscape, where everything becomes grainy and uncertain. The Planck scale is not simply small. It is the gateway between classical physics and quantum reality. When Einstein first revealed the idea that gravity is the curvature of space-time, he changed our perception of reality at large scales. But when we combine his work with quantum mechanics, we begin to glimpse a deeper truth. Gravity may emerge from the quantum structure of space-time itself. The force we experience as the attraction between massive objects might be the visible echo of invisible quantum interactions. If this is correct, then gravity is not fundamental. It is the consequence of something deeper. At this point, we confront the possibility that nothing about space or time is what it appears to be. The passage of time might arise from the rearrangement of quantum information. The shape of space might emerge from a network of quantum links. Gravity might be a statistical effect, not a fundamental law. Yet all of these ideas remain theories. The Planck scale is too tiny for direct experiment. No particle accelerator on Earth can reach the energies required to probe these lengths. Even the most powerful collider ever built operates at energies trillions of times lower than the Planck energy. We cannot yet build a device large enough or powerful enough to observe the Planck scale directly, so we use the universe itself as our laboratory. Black holes, neutron stars, and the earliest moments after the birth of the cosmos are the only places where the Planck scale becomes relevant. In those extreme environments, gravity approaches its maximum. Quantum rules rise from the tall depths. Somewhere inside a collapsing black hole, or within the first sliver of time after the Big Bang, space-time reached the Planck limit. Something unforgettable must have happened. What occurs when gravity reaches that limit? Does space-time resist further collapse? Does it rebound? Does it branch into a new region of space? Does something entirely new come into being? The answers lie ahead. A black hole begins as a star. Not just any star, but one that contains many times the mass of our Sun. During its lifetime, that star burns hydrogen into helium, then helium into heavier elements, generating outward pressure that pushes against gravity. This balance holds the star together, but eventually the fuel runs out. When the fusion furnace in the core goes dark, gravity has no opponent. The collapse begins. Layer after layer falls inward. The core becomes denser and hotter until the pressure becomes so intense that even the atoms cannot withstand the crush. At first, electrons are forced into protons, creating neutrons. The star becomes a sphere of densely packed neutrons, a neutron star, an object so compact that a teaspoon of its material would exceed the mass of a mountain on Earth. But even this extraordinary structure provides only a temporary halt. If the dying star contains enough mass, gravity overwhelms even the pressure of neutrons. The core collapses again, beyond all known forms of matter. The collapse does not stop. It races inward towards something far stranger. If gravity were just a pulling force, we might imagine that the collapsing matter falls to a point in space. But Einstein showed that gravity is not a pull. It is the bending of space itself. During collapse, space curves more steeply. Time slows near the collapsing core. Light struggles to escape. Eventually, a boundary forms around the collapsing matter. This boundary is called the event horizon. Nothing inside this region can escape back into the universe. Inside the horizon, every path leads inward. Space funnels all objects toward the center. Time guides motion to the same fate. It is not that objects fall toward the center by choice. The geometry of space-time forces the direction. From the outside, time appears to freeze. As matter falls toward the event horizon, clocks seem to slow. Light becomes stretched. The falling star appears to hover on the edge, never quite disappearing. But from the perspective of the matter itself, the collapse continues unimpeded. There is no sense of slowing. Time flows normally. The star collapses deeper and deeper into the curvature that gravity creates. General relativity predicts that the collapse has no bottom. The matter shrinks toward a point with zero volume. Density becomes infinite. Space-time curvature becomes infinite. Mathematics does not merely suggest this, it demands it. But this conclusion contains a silent alarm. Infinite density is not a physical state. It is the universe telling us that our model of gravity has reached a place where it can no longer describe reality. Infinity means we have asked the wrong question. There is a reason the idea of infinite curvature is troubling. The fabric of space-time is not supposed to tear. It bends. It stretches. It flexes. Yet general relativity pushes it into a shape that can no longer exist. If space-time continued to compress without limit, it would not merely bend. It would collapse into nothing. Infinities show up only when our description of nature breaks. We can be certain of one fact. Whatever happens at the center of a black hole is not a true singularity. It is simply a place where our current theories stop working. To understand why this happens, we must step inside a black hole in thought. Not physically. No human can cross an event horizon and report back. Even information cannot escape from within, but we can follow the mathematics. Once inside, the idea of standing still becomes absurd. Space itself flows toward the center faster than any object can move outward. It is like being caught in a river that accelerates as you approach a waterfall. No matter how hard you swim, the current wins. Close to the center, the curvature of space-time becomes extreme. Tidal forces stretch objects along one direction and compress them in another. In fiction, this effect has been called spaghettification because the body would be elongated into a thin thread. But this is just the fate of ordinary matter on the approach. It tells us nothing of what happens at the end. As we continue downward, we reach scales where the smooth geometry Einstein described begins to break down. Space-time approaches the Planck scale, too small for classical geometry to make sense. Quantum fluctuations erupt. Distances lose meaning. Time no longer flows the way it does at large scales. The gentle curvature near the edge is replaced by roiling turbulence. At this point, the gravitational collapse confronts a limit. If gravity grows stronger only by demanding more curvature, and if curvature cannot exceed the capacity of the smallest quantum grain of space-time, then collapse cannot continue. Something must resist further compression. Something must take place within the very heart of the black hole that prevents infinity. It may be violent, it may be subtle, but it must happen. Physicists once assumed that black holes were static dead ends, but advances in quantum theory have forced a new view. Black holes are not voids, they are active physical systems. They hold information, they radiate energy, they evolve, they might one day evaporate. A black hole is not a hole. It is an object whose interior may hide an astonishing form of matter or geometry. The closer we examine black holes, the clearer the truth becomes. They are laboratories where gravity approaches its absolute limit. Inside a black hole, time and space trade roles in a way our minds struggle to accept. Outside the event horizon, we can choose where to go in space. We may walk north or south, climb a hill, or stay where we are. Time, on the other hand, always moves forward. We have no power to reverse it. But once an object crosses the event horizon, those roles shift. Inside a black hole, the direction toward the center becomes as unavoidable as the future. Reaching the center is not a matter of being pulled inward. It becomes a matter of moving forward in time. No force can stop this. Progression because every possible path leads inward. It is not a choice. It is fate written into geometry. As the collapse narrows into a smaller and smaller space, the equations of general relativity insist that space-time curves without limit. This leads to the traditional picture of a singularity, a point where the curvature becomes infinite. But infinity is a sign of surrender. When we see infinity in physics, it means that the theory has reached a boundary where it no longer describes nature. It is the place where our mathematics breaks before reality does. Nature rarely permits infinities. The universe has limits. Those limits may be unimaginably extreme, but they exist. The Planck scale is one such limit. At that scale, space-time behaves more like a quantum system than a smooth surface. Gravity cannot be described merely as curvature, because curvature itself no longer behaves in a continuous way. It becomes granular, it becomes quantized, it becomes a structure that may resist further collapse. If space-time has a smallest unit, then the interior of a black hole must be governed by that discreteness. When the collapsing core reaches densities where the gravitational force approaches the Planck force, the collapse must slow. The core may still be unimaginably dense, but it can no longer shrink without limit. The curvature cannot deepen forever. The pressure of quantum geometry begins to push back. At this threshold, classical physics becomes blind. The collapse does not go quiet, it becomes violent. Matter that was once coherent, plasma becomes so compressed that its identity dissolves. Quarks and gluons, the particles that make up protons and neutrons, may be forced into a state of pure energy. The mass that once fueled a star becomes information trapped inside a region of extreme curvature. If the collapse is halted at the Planck scale, then the center of a black hole is not a point. It is a region where the rules of time and space break open. Some physicists propose that deep inside the event horizon, the collapsing matter encounters a quantum wall. Instead of continuing to contract into zero volume, the matter reaches a state of maximum density. The pressure becomes so intense that quantum mechanical effects overpower the classical tendency to compress. It is at this juncture that gravity hits its ceiling. Imagine dropping a stone into the ocean. The stone sinks until it reaches the bottom. A black hole collapse may mirror that story. Gravity acts like the ocean pulling matter downward. The event horizon is the surface of the water. The collapse continues until it reaches the quantum bottom. But a deeper truth lurks beneath that metaphor. When matter reaches that bottom, it may not simply stop. It may rebound. It may generate a new space-time region within the black hole, perhaps even a universe. The surface we call the event horizon hides every possibility. No one outside can witness what occurs beyond it. For an observer, falling in time flows normally. The fall continues and nothing exceptional is noticed as the horizon passes. But from the perspective of the outside universe, the fall appears to freeze forever. The object becomes more and more red, shifted, until it seems to vanish into darkness. The two views cannot be reconciled within classical physics. The conflict hints that our ideas are incomplete. We know that black holes hold information. Stephen Hawking showed that black holes emit radiation. This radiation is feeble for large black holes and grows stronger as they shrink. Eventually, the black hole should evaporate entirely. The question then becomes what happens to the information that fell inside. For many years it appeared that information might be lost forever, but quantum mechanics forbids that outcome. Information cannot simply disappear. So black holes must preserve it somehow. This realization pushed physicists to re-examine the interior. Perhaps the region inside the horizon is not a one-way journey to an impossible point. Perhaps it is a storage vault where information persists in a form we do not yet understand. The collapse leads to a state where quantum geometry holds everything in balance. In this vision, a black hole is not the end of matter, It is the beginning of quantum gravity. Without black holes, we might never suspect that gravity has a maximum strength. But when we allow gravity to run wild, it leads us to a paradox. General relativity insists on infinite curvature. Quantum mechanics forbids infinite compression. The apparent contradiction is not a weakness. It is a sign that both theories are part of something deeper. Black holes are not cosmic traps. They are experiments the universe performs on itself. They take ordinary matter and push it to the limits of physics. At the threshold of the Planck scale, gravity reaches its maximum. Beyond that point, a new description of spacetime waits. Every black hole hides a secret. The universe whispers that somewhere deep in the heart of those shadows, the rules change. Space stops bending. Time stops shrinking. Gravity stops growing. What lies beyond that boundary may redefine our understanding of reality. To understand what happens when gravity reaches its ceiling, we must search for a new language. General relativity speaks with the voice of continuous geometry. Quantum mechanics speaks with the voice of probabilities. At ordinary scales, the two do not interfere. They coexist like neighbors who do not speak. But in the heart of a black hole, or in the first moments of the universe, those two worlds collide. Gravity becomes so intense that quantum effects cannot be ignored. Quantum effects become so wild that geometry cannot stay smooth. The two theories crash together, and neither survives intact. Physicists have spent decades trying to connect these two visions into one theory, a theory of quantum gravity. It is not a simple project. To unite them, we must imagine something that nearly breaks the mind. The stage, on, which physics takes place, may not be fundamental. Space and time themselves may emerge from deeper rules. If that is true, then gravity is not a force or even a curvature. It is a consequence, a ripple in something more primal. The first major attempt to describe this deeper world is string theory. In string theory, every particle is essentially a vibration. The particle we call an electron is a vibration of one frequency. The particle we call a quark is a vibration of another. Matter and energy are the music these strings create. But strings do not vibrate in ordinary space. They vibrate in a space that may contain more dimensions than we can perceive. These extra dimensions might be curled up so tightly that we cannot detect them. They may be hidden inside the fabric of the reality we see. String theory allows gravity to emerge naturally. A particular vibration of a string behaves exactly like a particle that carries the gravitational interaction. If this is true, then gravity is born from the vibrations of these strings. It is not fundamental. It is a side effect. The strength of gravity depends on the shape of the dimensions that surround the strings. This raises a remarkable possibility. If those hidden dimensions change curvature or form, then gravity could change strength. It might even reach a maximum because the underlying geometry refuses to deform beyond a certain point. In that vision, the ceiling of gravity exists because the structure beneath spacetime cannot stretch beyond a limit. Another approach to quantum gravity takes a very different path. It is called loop quantum gravity. Instead of imagining strings vibrating in many dimensions, this theory imagines that spacetime itself is constructed from tiny loops of geometry. These loops form a network that defines distances and areas. Space is not continuous. It is granular, like tiny links in a chain. Time itself becomes quantized. If space is made of loops, then space cannot shrink into a point. These loops have minimum size. At the deepest level, space-time is not smooth, it is a web. The curvature of that web eventually stops increasing. Gravity reaches its maximum because the loops resist further compression. Loop quantum gravity makes a bold prediction. Inside a black hole, the collapse halts when the matter reaches a point where the loops cannot compress further. Instead of shrinking to a singularity, the collapsing core rebounds. This creates something known as a Planck star. A Planck star is a theoretical object that forms when matter reaches the maximum density allowed by quantum rules. Time flows differently inside the black hole. To us on the outside, the rebound might take billions of years. But from the point of view of matter inside the horizon, the rebound could be almost instant. The collapse becomes a bounce. There is still another perspective. Some physicists believe that gravity does not arise from particles or loops. Instead, gravity emerges from information. In this view, the universe behaves like a complex system of data. Entropy becomes the key. Entropy is a measure of information. It also measures disorder. When we stretch a rubber band, we increase its tension. When we compress information, we increase entropy. Gravity, in this view, arises from the natural tendency of systems to increase entropy. Matter moves in a way that maximizes information. The paths that objects follow through spacetime are the paths of greatest entropy. This picture leads to a startling interpretation. Gravity might be an entropic effect, not a force, not a curvature, but the statistical behavior of information trying to arrange itself. If that is true, then gravity must have an upper bound. There must be a maximum amount of information that can exist in a region of space. When that limit is reached, gravity cannot increase further. It would be like reaching the maximum possible tension in a net. No matter how much more we pull, nothing happens. The structure simply cannot stretch beyond that limit. Three very different approaches: strings vibrating in many dimensions, loops woven into the fabric of space-time, information shaping curvature through entropy. They disagree on almost everything, yet they agree on one key point. Gravity cannot continue to grow without limit. There must be a ceiling. Beyond that ceiling, the universe must reveal new laws. To reach that ceiling, we must follow matter into the places where gravity eclipses every other interaction. Black holes are the clearest path. They are the crucibles in which the geometry of the universe is pushed to its limit. When matter collapses inside a black hole, everything we know strains to the breaking point. Curvature deepens, tidal forces increase, time slows. Eventually, the collapse reaches a scale where classical geometry becomes meaningless. The quantum structure of space-time takes control. At that moment, gravity hits its maximum. No one knows what happens then. Perhaps the matter rebounds. Perhaps it tunnels into a new region of space-time. Perhaps the interior of the black hole becomes a birthplace of new universes. Whatever happens beyond the ceiling of gravity does not lie within general relativity. It lies within the realm of quantum gravity. Quantum gravity is not a single theory. It is a question so deep that the universe itself seems to protect the answer. Every approach we have built so far is a story told in the dark. Each one reveals a different shadow of the same unseen shape. We know that gravity must have a maximum strength because the universe refuses to allow infinities. We know that quantum mechanics must take over at the smallest scales because the smooth surface of space-time begins to quake. We know that general relativity cannot explain what happens when matter is compressed beyond a certain point. Yet we continue searching for the bridge between these truths. In string theory, the fundamental entities are one-dimensional strings that vibrate in a space with many hidden dimensions. The vibrations determine the type of particle and the force it represents. Gravity emerges as a vibration that cannot be confined to our familiar three spatial dimensions. It leaks slightly into the hidden ones. That leak explains why gravity is so much weaker than the other interactions. They are trapped in our dimensions while gravity spreads its influence. In this picture, the strength of gravity depends on the shape of these hidden dimensions. If space tries to curve too tightly, the hidden dimensions resist like a coiled spring. That resistance could cap the strength of gravity. Loop quantum gravity speaks in an entirely different dialect. It claims that space-time is made of finite units, tiny chunks of volume. In this view, you cannot divide space forever. Eventually, you reach a unit that cannot be split. Beyond that point, the collapse inside a black hole encounters a lower bound. Matter reaches a state where the curvature of space-time cannot deepen further, because the loops that define geometry cannot compress. When collapse reaches that point, gravity no longer strengthens. Instead, energy and information are stored in the loops themselves. The black hole becomes a vault of geometry. The entropic view reimagines gravity even more radically. It claims that gravity emerges from the tendency of systems to increase disorder. If you place a ball near a cold region of space-time and a warm region of space-time, the ball moves in a direction that increases overall entropy. That motion looks like a gravitational attraction, but there is no fundamental force. Instead, entropy shapes the motion of matter and defines the curvature of space-time. In this story, space-time is not a fabric. It is a bookkeeping system for information. The bending of space-time is the rearrangement of data. Each of these ideas sounds overwhelming, but they share something profound. They remove gravity from its pedestal. Gravity becomes a consequence, not a cause. It arises from deeper principles. And if gravity emerges from something deeper, then it must have limits defined by that deeper structure. Consider an archway carved from stone. The arch appears to hold itself up by magic. But the arch is not truly self-supporting. It is held up by the forces distributed through the shapes of its stones. The strength is not inherent in the arch itself, but in the pattern of arrangement. Gravity might be the same. It may not be a force. It may not be a curvature. It may be an arrangement, a pattern formed by the underlying quantum structure of space-time. If that pattern reaches a maximum configuration, the strength of gravity reaches a maximum as well. Now picture matter collapsing inside a black hole. At first, gravity compresses it easily. The core becomes smaller and denser. Space curves more sharply. Time slows. But deep inside, near the Planck scale, the structure beneath space-time pushes back. The underlying quantum elements resist the collapse. The pattern of information that defines the geometry cannot compress further. Gravity reaches its ceiling. Collapse stalls. What happens next is uncertain. In loop quantum gravity, the collapsed matter rebounds and forms a Planck star. A Planck star would be incredibly small compared to the original star. But to matter inside the black hole, the rebound could occur rapidly. The collapse could reverse, like a spring compressed to its limit. But time dilation is extreme near and inside a black hole. For an observer outside, the bounce might take longer than the current age of the universe. That tension between internal time and external time creates a strange duality. Inside the black hole, events unfold. Outside the black hole, nothing seems to change. In the entropic view, information at the event horizon is preserved as a holographic record. The idea suggests that the interior of a black hole is not the true repository of information. Instead, information might live on the surface area of the horizon itself. The smaller the black hole becomes, the less area the horizon has. When the black hole evaporates through Hawking radiation, the information somehow returns encoded in the radiation. If this is true, then black holes are not destroyers of information. They are processors. They rearrange information and reveal it again over unimaginable spans of time. If string theory is correct, then inside the black hole, lies a place where extra dimensions become relevant. Perhaps the collapsing matter does not crush into a smaller volume of our familiar space. Perhaps it tunnels into those hidden dimensions. The black hole interior may be a crossroads between dimensions. Instead of reaching one impossible point, the matter may spread through unseen geometric corridors. Gravity may reach its limit because the deeper structure of space distributes the collapse into dimensions beyond our perception. We cannot choose between these possibilities yet. We do not know which one is true, but all of them point to the same conclusion. When gravity reaches the Planck limit, the world changes. Spacetime does not tear. The collapse does not create an actual infinity. The universe does not allow an equation to override reality. Something new emerges. We once believed that black holes were the final word. They were the great endings of matter and energy. But every new discovery shows the opposite. Black holes are the beginning of quantum gravity. They are the gates where space-time transitions into its deepest form. They are the places where the familiar world is peeled away and the fundamental nature of reality is revealed. The universe does not fear extremes. It uses them to teach us. Black holes are not monsters. They are the boundary markers of knowledge. Imagine falling into a black hole. Not drifting, not floating, but falling in a way that cannot be stopped. The fabric of space pulls you inward, not as a force, but as a direction of time itself. Space narrows, time stretches. Every heartbeat becomes heavier. Every motion grows slower. At first, the fall feels smooth, as if nothing unusual is happening. But then you begin to sense a pressure building, not around you, but within the very structure of reality. The closer you move toward the center, the more violent the curvature becomes. Gravity grows without mercy, yet something unexpected waits ahead. For decades, we believed that nothing could interrupt this collapse. Matter would be crushed past atoms, past nuclei, past the existence of individual particles. Everything would fall until it reached a place of infinite density. The idea of a singularity was accepted, even though no one had ever seen such a location, and the idea itself violated the laws of physics. A point of infinite density is not an explanation. It is the moment a theory admits defeat. But a growing body of evidence suggests that collapse may not continue forever. Deep within the black hole, a new kind of matter may be born. Not matter as we know it, not atoms or quarks or particles, something defined by the quantum structure of space-time itself. When the collapsing core reaches a critical density, gravity reaches its maximum strength. At this point, something extraordinary happens. Collapse halts. Think of gravity as a hand pressing inward. Quantum geometry becomes a hand pressing back. When those hands meet, collapse cannot progress further. In that moment, space-time becomes compressed to the smallest possible unit. The loops or strings or informational quanta that form the foundation of space cannot be squeezed smaller. Space-time stiffens. The collapse reaches the Planck limit. This limit is not soft, it is absolute. In loop quantum gravity, the core that forms at this moment is called a Planck star. It is tiny compared to the original star, but massive beyond comprehension. Its density reaches the maximum the universe allows. Time inside this region behaves strangely. To an outside observer, time near a black hole moves slowly. At the event, horizon time appears to stop. But within the deep interior of the black hole, time continues. The collapsing matter experiences the bounce quickly, almost instantly. Meanwhile, the outside universe witnesses nothing at all. The collapse and rebound are hidden by the enormous time dilation. To understand this difference, we must imagine the interior of the black hole not as a space, but as a timeline. The inward direction is not where collapse happens. It is when collapse happens. Moving deeper, means moving forward in time. The bounce that reverses collapse is like reaching the end of that timeline. Once the Planck limit is reached, time cannot continue in that direction. A new direction must open. The matter rebounds. At first, the rebound is quiet. It does not explode. It expands slowly, held back by the weight of the geometry around it. To us, outside the black hole, the rebound is hidden behind the event horizon. Even if it happened quickly, time near the event horizon slows so dramatically that billions of years may pass before we glimpse the change from the outside. The Planck star could be expanding while the black hole still appears unchanged. We would never notice until the horizon finally shrinks, either by evaporation or some other process, and reveals the interior. The idea that collapse reverses is not science fiction. It is a direct consequence of combining quantum mechanics with general relativity. The collapse can continue only until spacetime reaches its maximum curvature. After that, quantum pressure forces expansion. The universe does not choose infinite density. It chooses a transformation. This rebound does not violate any known law. Conservation of energy holds. Information remains preserved. Nothing vanishes. The Planck star becomes a reservoir of everything that fell inside the black hole. The information remains encoded within the quantum structure of spacetime. This concept holds profound implications. If black holes eventually release the stored information, the universe becomes a cycle of collapse and rebound. A star dies, it collapses, it forms a black hole. Deep inside, the collapse halts. A Planck star grows. Eventually, a rebound begins. Energy and information emerge again, perhaps as radiation or perhaps in a form we cannot yet predict. Collapse does not destroy. Collapse transforms. The moment collapse reverses is not quiet. The mathematics suggests that inside the Planck star the pressure is unimaginable. But pressure here is not the crushing force we experience in everyday life. It is the resistance of space-time itself. Think of it like compressing a spring. Each moment of collapse stores energy in the geometry of space-time. When the quantum limit is reached, the spring does not compress further. It is forced to release. The rebound might be subtle, or it might be violent. Some researchers suggest that a rebounding black hole could generate a burst of energy so intense that it becomes visible across the cosmos. Short, unexplained flashes of high-energy radiation, known as gamma bursts, have been discovered. Some of them last only fractions of a second. Their origin remains uncertain. Could Planck star rebounds be responsible for some of these cosmic flashes? No one knows. The idea is young, but nature leaves clues. If collapse can reverse, then the universe itself may have been born through such a rebound. Our cosmos may be the aftermath of a previous collapse. The beginning of time could have been a bounce, not an origin from nothing. A rebound from a previous space-time that reached a maximum curvature, then expanded into ours. The universe may be filled not with singularities, but with transformations. The Planck scale prevents infinities. The quantum structure of space-time prevents destruction. Inside the deepest depths of a black hole, collapse may not be an ending. It may be the beginning of something new. At the limit of gravity lies a doorway. As the rebound begins, the interior of the black hole becomes a place where ordinary language fails. The rules we grew up trusting begin to fade. Inside a Planck star, the familiar separation between space and time dissolves. Instead, there is only evolution of geometry itself. That evolution carries information from a compressed state toward a state of expansion. But this motion does not resemble expansion in our universe. It is more like unfolding. Everything that fell into the black hole during its lifetime becomes part of the quantum structure of the Planck star. The mass of planets, the heat of collapsing plasma, the magnetic fields of the star that once burned all of it becomes information. The Planck star stores that information not as matter, but as configuration. It is memory written into the deepest levels of space-time. From within the Planck star, the rebound feels quick. Time moves normally. But from the outside universe, time is stretched and slowed until moments last near forever. A process that might take a fraction of a second inside could appear as billions upon billions of years to someone outside. If the expanding interior pushes against the horizon, the outside world will not see it until the horizon shrinks. And the horizon shrinks very slowly through Hawking radiation. Hawking radiation is like a whisper of evaporation. It steals mass from the black hole gradually. As the black hole loses mass, its event horizon shrinks. The smaller the horizon becomes, the faster the radiation increases. This forms a strange connection. The collapse that once seemed final becomes the seed for an expansion that waits patiently hidden behind the horizon until the universe has aged enough for the horizon to reveal what lies inside. The Planck star waits in silence. When the radiation has removed enough mass, the horizon shrinks until it touches the expanding core. The moment that happens, the interior and exterior worlds reconnect. Everything once swallowed begins to return. Information that seemed lost becomes free. The Planck star becomes visible. The rebound becomes an eruption. This moment challenges our deepest assumptions. For all of science history, we believed black holes were places where matter vanished. Hawking radiation added a subtle correction by suggesting that black holes slowly evaporate. But the Planck star hypothesis goes further. It says that nothing is lost. The matter does not vanish into a singularity. It remains stored until the horizon retreats enough to release it. Collapse and evaporation become two sides of one continuous story. A star dies in the most violent collapse imaginable, yet the collapse eventually reverses and becomes an outflow. Imagine watching a black hole across unimaginable spans of time. First it forms when a massive star dies. Then it sits silently in the darkness. It consumes matter from its surroundings. It pulls gas and dust and unlucky stars into its horizon. For eons, nothing seems to happen. But deep inside the black hole, the Planck star grows slowly. It expands at its own pace. The event horizon remains far outside the expanding region, and nothing escapes. Then one day, the horizon itself shrinks. The Planck star touches the boundary. Suddenly, the black hole brightens. A burst of energy surges outward. It is the rebirth of matter. Some researchers believe that the brief bursts of high-energy radiation we detect from faraway galaxies might be the ancient final moments of black holes releasing Planck stars. These bursts last mere fractions of a second, but their power is immense. They emit more energy in that moment than entire galaxies emit in long periods of time. We do not know if these bursts are truly the echoes of Planck stars. But the possibility forces us to look at black holes differently. They may not be graves. They may be seeds. The idea that collapse reverses has implications beyond black holes. If collapse can reverse, it may mean that the universe itself began from a rebound. Instead of a beginning from absolute nothingness, the birth of our cosmos may have been the moment when a previous space-time reached the maximum limit of gravity and could collapse no further. That moment of reversal may have ignited expansion. The Big Bang may have been a bounce. To imagine that possibility is to accept that time may not begin at a point. Time may be part of a loop. The universe collapses under the weight of its own matter until quantum gravity halts the compression. Then it expands again. The cosmos becomes a cycle. Birth and death are not opposites, they are phases. Everywhere we look, nature reuses matter. It reshapes energy. Stars are born, burn, collapse, and recycle their materials. On Earth, ecosystems recycle nutrients endlessly. Water cycles between ocean, sky, and land. Life recycles atoms continuously. Perhaps space-time itself recycles universes. yet we must remain cautious. The Planck star idea, though supported by serious research, is not yet proven. The evidence we have is indirect. We see the absence of singularities in our deeper equations. We see the mathematical resistance to infinite density. We see in quantum theory that collapse must halt. But we have not directly observed a Planck star. We do not yet possess the instruments capable of such observation. Our only witnesses are the far distant flashes of gamma radiation and the stubborn belief that the universe avoids infinities. We stand at the edge of our knowledge. The collapse reversal is the most dramatic consequence of quantum gravity theories that avoid infinities. But the universe may have even more radical surprises waiting. If gravity reaches its maximum and collapse reverses, then the idea of space-time itself must evolve. A Planck star is not an object in the ordinary sense. It is a region where geometry reaches a limit and changes direction. It is the moment when space-time breathes. In every collapse lies a hidden beginning. In every ending lies a quiet promise. When gravity can no longer grow, the universe does something astonishing. It changes the rules. There are moments in physics when the known world seems to crack open. Black holes are such moments. They push gravity toward its maximum strength until space-time bends so sharply that the laws we trust begin to fail. Inside their silent darkness, reality becomes strange. We have followed gravity to the point where collapse halts and rebounds. But another question waits in the shadows. What if gravity does not simply stop? What if it pushes space-time so far that space-time itself changes topology? Topology is the deep structure of space. It describes how space is connected. If gravity could change that structure, then a black hole might be more than a pit. It could be a doorway. To understand what that means, we must imagine space-time as something flexible. Not just flexible in shape, but flexible in structure. A sheet can bend without tearing. A rubber band can stretch without breaking. But if you push any material far enough, it reaches a point where bending is no longer possible without altering its form. Wood bends only so far before it splits. Ice bends only so far before it cracks. If space-time is a structure, perhaps gravitational collapse pushes it toward a similar limit. When gravity intensifies, the curvature of space deepens. Light bends around the curve. Matter sinks along the curve. Time slows near the curve. If the curvature deepens further, every path leads inward. Yet what happens if curvature tries to go beyond that extreme? Quantum rules may prevent infinite curvature, but something else might happen at the ceiling. Space-time might rearrange itself. Physicists exploring this possibility speak of space-time not as a sheet, but as something more dynamic. Instead of picturing a rubber sheet with a funnel, we imagine space-time as a network of relationships. If the bonds between regions of space change, then space can alter its connectivity. In that transformation, 2 points that were once distant may become close, or 2 regions that were once connected may separate. Topology alters. This leads to an astonishing idea. Inside a black hole, gravity might pull space-time so tight that it changes its fundamental connections. Instead of merely compressing matter, the collapse might fold space into a tunnel. In ordinary language, this is what we call a wormhole. A wormhole is not a hole in space. It is a shortcut in the structure of space-time. Imagine walking around a globe. The long path is along the surface. But if the surface could fold 2 distant points together, you could reach your destination instantly. A wormhole does not shorten distance, it changes distance. Einstein himself predicted the mathematical form of wormholes. The simplest version involved 2 black holes connected by a bridge. Physicists call that structure an Einstein-Rosen bridge. In its classical form, the bridge is unstable. It pinches off too quickly for anything to cross. But that conclusion assumes space-time remains smooth. If quantum structures prevent collapse beyond a limit, then perhaps the bridge does not pinch off. Perhaps the Planck limit holds the throat of the tunnel open. Let us imagine falling into a black hole where space-time is approaching its maximum curvature. The collapse speeds up, time stretches, light spirals inward. Suddenly the topology changes. Instead of a single shrinking point, we encounter a throat, a region where space narrows like the neck of an hourglass. Inside that throat, space continues. It leads not to destruction, but somewhere else. This possibility forces a new way of thinking. Gravity does not simply crush, it rearranges. When space-time cannot compress further because of quantum limits, it might change form. A topological transition could occur. That transition could connect the interior of a black hole to a new region of space-time. The black hole would no longer be an ending, it would be a junction. If such a connection exists, what lies on the other side? It might be another region of our universe. It might be an entirely separate universe. It might even be a region where time flows differently. The geometry of space-time determines what is past and what is future. A change of topology could alter that flow. But we must remain cautious. Even if a wormhole forms inside the interior, its opening might remain hidden behind the event horizon. No signal could return. The connection might exist but be inaccessible. In that case, wormholes would be like bridges in a locked room. They exist, but no one can use them. Still, the possibility changes our understanding. A black hole might not be a dead end, but a place where space-time reorganizes. Another idea emerges from theoretical studies. If space-time is pushed too far, gravity might not only create new connections but sever old ones. Space could be torn and reattached in new ways. Some physicists call this a topology change event. It is not a violent explosion, but a reconfiguration, a restitching of space-time. The deeper we push our imagination, the clearer it becomes that gravity does not simply pull. It shapes, it carves. At its maximum, it transforms. In this new picture, a black hole no longer hides a singularity. It hides a transition, a phase change in the geometry of the universe, a boundary where classical space ends and quantum space begins. At that moment, gravity stops being gravity. It becomes something else, something fundamental that we have not understood. What waits beyond that limit is still unknown, but we are close, very close. The idea that gravity could reshape the architecture of space-time forces us to confront an unsettling truth. We are used to thinking of the universe as a place with fixed geometry. Distances have meaning, directions have meaning, the shape of reality feels stable. But when gravity approaches its maximum strength, that stability may vanish. Space-time may behave not like a smooth surface, but like an adaptable structure that shifts in response to extreme curvature. Inside a black hole, the curvature deepens until time itself becomes a pathway to the center. Every direction of motion becomes a direction toward greater compression. From the outside, the horizon appears to be a simple boundary, but from within the horizon, the story becomes more dramatic. Gravity pushes space-time toward the edge of what it can endure. If collapse halts because of the discrete nature of quantum geometry, it leaves open a deeper question. What if instead of halting smoothly, space-time is forced to rearrange? When we try to picture such a transformation, our minds reach for visual analogies. We imagine a sheet of paper bent into a cylinder or a ribbon twisted into a loop. But these images are too simple. Space-time is not a surface floating in a higher dimension. It is the arena of existence itself. A change in its structure does not happen within space. It creates the definition of space. Some physicists suspect that when collapse reaches the Planck limit, a tunnel forms. This tunnel does not have walls or rails or openings. It is a region where distance changes meaning. The distance between 2 points is determined by the geometry of spacetime. If that geometry changes, the distance can change as well. 2 locations once separated by billions of kilometers could become neighbors inside the throat of a wormhole. In such a tunnel, direction becomes ambiguous. Forward might lead sideways. Down might lead elsewhere. In this vision of reality, a black hole is not a prison. It is a gateway into altered geometry. The journey is not chosen. It is dictated by the structure of spacetime. If the tunnel leads to a new region of spacetime, then falling inward may be equivalent to being transported. A traveler crossing the horizon could be carried into another part of the universe, or even into a new universe entirely. This is not fantasy. It is what the mathematics allows if quantum rules prevent the collapse of geometry into a singularity. The collapse may reach the maximum curvature and then force a topological shift. The smooth funnel becomes a passage. Instead of a bottom, there is a doorway. Yet gravity does not give such a passage freely. The geometry of a wormhole is delicate. The equations show that maintaining an open passage requires something exotic. The tunnel must resist collapse. It must push outward while gravity pulls inward. In classical physics, nothing behaves that way. Matter cannot provide that kind of outward pressure. But at the Planck scale, matter loses identity. Geometry becomes fluid. Quantum fields become turbulent. The interior of a black hole is the one place where exotic quantum states could appear naturally. If the tunnel opens, it may not last. The moment curvature relaxes, the throat could close. The geometry could snap back. The passage would end. Anyone or anything inside would continue onward into the new region of spacetime without the ability to return. A one-way bridge. There is another possibility. Instead of forming a tunnel, gravity might tear spacetime into separate pieces. Imagine the universe as a connected network. Each point of space is tied to others through invisible relations. If collapse forces too much curvature into too small a region, those relations might be severed. The interior of the black hole could become a region disconnected from our universe. A new spacetime bubbles off like a droplet separating from a wave. The black hole becomes a bud of a new cosmos. The event horizon becomes its boundary. To the outside universe, the black hole evaporates. To the interior universe, that evaporation marks its birth. Cosmologists have asked a wild question. Could every black hole in our universe be the seed of a new universe? If so, then our universe might itself be the interior of a black hole formed in another universe. The beginning of time in our cosmos might be the moment collapse reached a quantum limit in a larger parent universe and bounced or branched. In that moment, space-time changed its topology. It separated and formed us. This idea is not impossible to test. If our universe were born inside a black hole, then certain imprints might exist in the distribution of galaxies or in the pattern of the cosmic microwave background. Researchers have searched for signs of such imprints. None are confirmed yet, but the search continues. If gravity truly pushes space-time to the brink of tear and rearrangement, then black holes are not cosmic endpoints. They are workshops. They are wombs of geometry. Inside them, gravity is not a force of destruction. It is a force of creation. Standing outside a black hole, we see nothing but silence. Light falls inward. Information disappears beneath the horizon. But inside the horizon, the greatest transformation in the cosmos may occur. The collapse approaches maximum curvature. Quantum rules intervene. Geometry shifts. A new region of space-time emerges. And yet we remain cautious. Many of these ideas live on the frontier between theory and speculation. The mathematics hints at what is possible, but observation has not yet revealed proof. We stand facing a darkness that hides the deepest secret of the universe. gravity might be the sculptor of space-time, but quantum geometry is the chisel. The question becomes clear. If gravity can reshape space-time when it reaches its limit, what prevents gravity from fading entirely? If gravity is emergent, if it comes into being from deeper rules, then perhaps at the edge of extreme conditions, gravity does not simply change shape. Perhaps it switches off. Gravity feels permanent. It shapes every orbit, every path, every structure in the universe. It holds planets around stars and stars inside galaxies. It sculpts the cosmos into spirals and clusters. Even when we cannot see its influence, we feel it in the way the world behaves. But permanence is not certainty. What if gravity is not fundamental? What if there exist conditions in which gravity fades or even disappears? To explore this possibility, we must step beyond the world we know and consider the existence of hidden dimensions. Not dimensions of imagination, but dimensions of space that are simply too small or too strange for us to detect. String theory suggests that the universe may contain extraspatial dimensions curled so tightly that we cannot perceive them. Yet wrapped inside those dimensions may be the deeper structure that gives birth to gravity itself. In everyday experience, gravity behaves predictably. It weakens with distance. It affects everything with mass and even energy. But in models that include extra dimensions, gravity does not stay confined to the space we see. It can spread. The other fundamental interactions remain trapped in a three-dimensional membrane of space. Gravity alone leaks into the hidden dimensions and becomes diluted. This leakage may be why gravity is weaker than the other forces. It is not truly weak, it is distributed. In a universe built this way, there may exist a threshold, a point where the curvature of space-time becomes so intense that gravity slips entirely out of our visible dimensions. A gravity switch-off event. Beyond this threshold, gravity may no longer act within the familiar arena of three-dimensional space. Instead, it disappears into the deeper geometry that defines the universe. Imagine a trampoline stretched tight. Place a heavy stone on the surface. The fabric bends, and anything rolling on the surface moves toward the stone. That is gravity as curvature. Now imagine that beneath the trampoline there is a second flexible sheet. If the stone becomes too heavy, the fabric tears or stretches downward into the deeper sheet. The surface above becomes flat, not because the stone disappeared, but because the weight changed layers. Something similar could happen when gravity reaches its limit. Instead of continuing to deepen curvature beyond the quantum threshold, gravity might shift its influence into extra dimensions. In our space, it would appear to switch off. Theoretical models known as brain-world scenarios attempt to describe this idea. In these models, our universe is a three-dimensional membrane floating inside a higher dimensional space. All matter and light are bound to our membrane. Gravity is different. Gravity is a vibration of space-time itself and can extend into the higher dimensional bulk. A black hole may be a region where gravity sinks into those deeper dimensions. The event horizon hides the boundary where the switch-off occurs. When curvature reaches the maximum allowed in our dimensions, gravity begins to slip away. As the collapse of matter continues inside a black hole, the space-time curvature becomes sharper. But if gravity spreads into higher dimensions, the curvature in our dimensions no longer increases. Instead, the geometry changes. The collapse does not sharpen into infinite curvature. It simply exits our dimensional layer. The interior becomes a doorway to another geometric region, and gravity no longer acts the way we understand. From our perspective, gravity switches off. This is not the same as saying that gravity disappears. It continues to exist. It simply no longer belongs to the geometry we occupy. The collapse does not stop because of a limit in force, but because the force changes domains. In the language of brain-world physics, the black hole becomes a well through which gravity drains. The greater the curvature, the deeper the drainage. Eventually, the gravitational influence inside the black hole might no longer be detectable within our space. This concept is difficult to imagine because our minds are trained to think of space as a container. But space is not a container. It is a structure, and that structure might have layers. Consider a drop of water on a leaf. It appears to hold its shape because the water clings to the surface. But if the drop becomes too large, it no longer clings. It rolls away. Gravity in our universe may cling to our dimensions only to a point. Beyond that point, it rolls off into the deeper geometry that surrounds us. If gravity can switch off, then the end of collapse inside a black hole does not require a rebound or a Planck star. Instead, the collapse becomes invisible to us because the gravitational effect no longer belongs to our space-time. The interior might continue evolving in dimensions we cannot access. The implications are enormous. If black holes are gateways where gravity leaves our visible universe, then every time a star collapses, it might connect our cosmos to another dimensional layer. Black holes become not only objects of extreme density, but transitions where gravity abandons its role in our space. We seldom consider that a fundamental force might have an upper limit. We assume gravity always works. But if gravity is emergent from geometry, then its behavior depends entirely on that geometry. At maximum curvature, the structure may change. And when the structure changes, the phenomenon we call gravity may cease. The gravity switch-off idea grows from a single observation. Every physical law we have ever trusted collapses when pushed to the extreme. Light once believed to travel instantaneously was found to have a finite speed. Time once believed to be absolute was found to be elastic. Space once believed to be flat was found to be curved. Why should gravity be the only force that retains infinite strength? Perhaps gravity feels infinite because we have not yet reached the place where it ends. Gravity switching off sounds like a betrayal of intuition. We expect the universe to obey familiar rules, no matter how intense the environment becomes. We expect collapse to continue until nothing remains. But that expectation is rooted in the physics of ordinary space. When we begin to explore a reality with more dimensions than we can sense, that expectation loses its foundation. The extra dimensions in string theory or brain world models are not side curiosities. They are the pillars that determine how gravity behaves. In our three-dimensional perception, gravity seems weak. It is far weaker than the electromagnetic interaction and countless times weaker than the strong and weak nuclear interactions. We assume that weakness is a flaw in gravity, but brain world models suggest something remarkable. Gravity is not weak. It is diluted, like a light that shines not only forward, but in all directions of a room. Some radiation spreads where we cannot see it. The portion that remains visible appears faint. When a star collapses into a black hole, the curvature of space-time concentrates gravity into an ever smaller region. In ordinary general relativity, that concentration has no limit. But if some portion of gravity is leaking into extra dimensions, then increasing curvature might accelerate that leakage. The closer the collapse gets to the Planck limit, the more gravity escapes our dimensional layer. Eventually, the collapse reaches a point where nearly all gravitational influence has shifted into deeper dimensions. In our universe, gravity seems to have vanished. It does not fight collapse anymore. It no longer pushes or pulls on anything within our space. The collapse becomes something external to our universe. From inside the black hole, it feels like falling into a deeper ocean. From outside, it feels like the black hole has simply stopped communicating. When physicists describe extra dimensions, they often imagine them curled tightly like loops only million trillion times smaller than the nucleus of an atom. But beyond those compact dimensions, some brain world scenarios propose large extra dimensions that stretch beyond our universe. Think of a thin sheet floating in a vast, invisible atmosphere. Light and matter are trapped on the sheet. Gravity has access to the atmosphere. A black hole would be a puncture where gravity flows into the space beyond. Inside that puncture, the very concept of distance in our universe becomes meaningless. We normally imagine the event horizon as a simple surface, a point of no return, where the escape velocity equals the speed of light. But in this deeper picture, the horizon is not simply a boundary. It is a transitional surface where our dimensional rules give way to a different structure. Crossing the horizon is like stepping into a region where gravity has alternative pathways of motion. The collapse does not necessarily continue deeper into our space. It continues deeper into a geometry we cannot access. This idea challenges our perception of finality. If gravity can vanish from our universe inside a black hole, then black holes are not endpoints. They are points of transfer. The matter inside does not need to rebound. It does not need to form a Planck star. It simply ceases to interact with our space-time. It migrates into the higher dimensional bulk. From our perspective, the collapse ends because the force that drives it has exited. This idea creates an even stranger question. If gravity can flow out of our universe through black holes, could gravity also flow in? Could new matter or energy slip into our universe from another region of space-time? If so, then the birth of our universe could have been the moment when gravity entered from a higher dimensional domain, creating a patch of space-time that began expanding from an initial point where energy emerged into our universe. In this vision, gravity does not just sculpt space-time, it allows space-time itself to be exchanged. Some researchers describe our universe as a membrane floating in a larger ocean. If two membranes collide or touch their surfaces, might exchange energy. That exchange would appear as a sudden burst of expansion. A beginning of time in one universe might be the echo of activity in another. If gravity switches domains during collapse, then black holes become conduits. They become cosmic drains in one direction and possible cosmic springs in the other. There are hints from observation that gravity may not behave as expected at very small distances. Experiments attempting to measure gravitational force at sub-millimeter scales have found irregularities. These deviations are small and uncertain, but they point toward the possibility that gravity might not obey our equations uniformly. Some measurements show that gravity behaves slightly weaker than predicted when distances become extremely tiny. Such a reduction could be the first sign that gravity is leaking into extra dimensions. If gravity can leave our universe under extreme curvature in a black hole, then the maximum strength of gravity is not dictated by force. It is dictated by geometry. Once gravity saturates our three-dimensional space, it escapes into deeper layers. The collapse no longer increases curvature here, because curvature is being relieved into another domain. This would solve the singularity problem without requiring a rebound. Instead of forcing space-time to become infinitely curved, our universe simply stops participating in the collapse. The collapse continues elsewhere. In that elsewhere, infinite curvature may not arise because geometry might be different. The emergence of a new branch of space-time could occur naturally. The death of a star could seed a new region of reality. Gravity would be the midwife. Even if this idea is correct, we face a barrier of perspective. Everything that enters the event horizon is hidden. To us, the horizon is not a physical surface. It is a collapse of communication. We see nothing inside. We can never know whether gravity rebounds or switches off or escapes into extra dimensions by direct observation. But we can observe how black holes evolve over time. If small black holes evaporate faster than expected, there may be clues that gravity has drained into dimensions we cannot measure. Perhaps the reason black holes radiate is that gravity begins to abandon our universe. Perhaps the interior is not a prison, but an exit. The most radical part of this idea is not that gravity might vanish. It is that gravity may not exist independently. It may, require spacetime to exist. When spacetime changes, topology gravity may not survive the transition. In one region of spacetime, gravity is a familiar companion. In another region, the rules of existence might be different. If gravity can switch off, then gravity can switch on. And that realization leads to something even stranger. If gravity is not fundamental, then something else must be. Something deeper. Something from which gravity arises as an emergent behavior. We are used to thinking of gravity as one of the basic ingredients of reality. We imagine the universe beginning with four fundamental interactions and gravity standing among them as an equal. But what if gravity is not fundamental at all? What if gravity does not exist on its own, but appears only as a side effect of something deeper? If that is true, then the maximum strength of gravity is not a limit of force. It is a limit of knowledge, a limit of information, a limit of how reality arranges itself. To understand this possibility, we must return to a simple but unsettling idea. The universe does not begin with space and time. It begins with information. What we call space may be built from the way information is organized. What we call time may be built from the sequence in which information changes. Gravity might be the result of information rearranging itself. The origin of this idea comes from an unexpected place. In the early 1990s, a physicist named Ted Jacobson explored the equations of general relativity and noticed something strange. He derived Einstein gravity not from geometry, but from thermodynamics. He showed that space-time behaves like a thermodynamic system. If you assume that the universe obeys the laws of entropy and heat, then Einstein equations appear naturally. Gravity emerges from the tendency of information to move toward equilibrium. He did not assume gravity. Gravity appeared. Years later, another physicist named Eric Verlinde took the next step. He suggested that gravity is not a force at all. He argued that objects move toward each other not because of attraction, but because such motion increases the entropy of the universe. The increase in entropy, the increase in information disorder, looks like gravity. Verlinde compared the behavior of space-time to a stretched rubber band. When information shifts, the rubber band contracts or stretches. The motion of planets, the falling of an apple, the rising of tides, may not be caused by invisible attraction, but by the way information seeks the most probable arrangement. In this view, gravity is not a law. Gravity is a consequence. Imagine holding a puzzle. The pieces are scattered on a table. You shake the table, and the pieces move toward positions that fit. Order does not appear because the pieces are pulled by a force. Order appears because the configuration that fits contains more information patterns that satisfy the rules of the puzzle. Gravity might behave the same way. Matter moves not because something pulls it, but because moving increases the possible arrangements of microscopic information. If this idea is correct, then gravity cannot be infinite because information capacity cannot be infinite. There is a maximum amount of information that can exist in a region of space. When you reach that limit, the structure can no longer rearrange itself. Motion no longer increases entropy. Gravity reaches its ceiling. This brings us to one of the most astonishing discoveries in modern physics. The maximum amount of information inside a region of space does not depend on the volume. It depends on the surface area. A region of space behaves like a hologram. Information that describes the interior is encoded on the boundary. A black hole follows this rule exactly. The maximum amount of information inside a black hole is proportional not to the volume, but to the area of the event horizon. Nature behaves as if reality is written on the surface. This fact is known as the holographic principle. It suggests that our universe might be a projection, not an illusion, a real projection from deeper rules that exist on a boundary we cannot see. If the holographic principle is correct, then gravity is the visible shadow of hidden information. When the arrangement of information on the boundary changes, the geometry inside changes. We experience that change as the curvature of space-time. Gravity becomes not the shape of space, but the bookkeeping of information. Now we can understand why gravity reaches a maximum strength. Information has a maximum density. When the interior of a black hole or the early universe attempts to compress beyond that, limit the boundary cannot store the extra information. It forces a change. The collapse halts, the geometry reshapes. Something new begins. This is not speculation from philosophy. This idea comes from one of the most powerful results in theoretical physics. In a theory known as ADS-CFT correspondence, a universe with gravity can be completely described by a universe without gravity that exists on its boundary. Everything with gravity inside the space can be mapped to pure quantum information on the edge. Space with gravity becomes equivalent to information without gravity. Gravity emerges from information. We look at space-time as a stage. But in the holographic view, the stage is the projection of information. When a star collapses into a black hole, we think matter falls inward. But information is not falling. Information is rearranging. The event horizon becomes the ledger where information is stored. And when quantum processes change the horizon area, gravity changes with it. If gravity emerges from information, then it can vanish when information is saturated. A ceiling in the storage capacity of the horizon becomes a ceiling in the strength of gravity. When collapse reaches the Planck limit, the horizon cannot store additional information. The geometry cannot curve further. A new behavior must appear. Collapse reverses. Gravity switches. Domains. Space-time changes topology. Every story so far points to one startling truth. Gravity is not the architect. Gravity is the shadow of architecture. We once believed that gravity creates space-time. Now we see that information might create both. We once believed black holes destroy information. Now we see that black holes store it. We once believed a singularity lies at the center. Now we suspect a transformation lies there instead. If the universe is built from information, then gravity is a language. And like all languages, it has grammar. It has limits. And if we push beyond those limits, the universe begins to speak in a different tongue. If gravity emerges from information, then the key to understanding its limits is not mass or curvature or motion. The key is entropy. Entropy measures how many microscopic arrangements correspond to the same macroscopic appearance. When a system evolves, it moves toward the configuration that allows the greatest number of microscopic possibilities. This is not preference or intention. This is mathematics. It is the universe choosing the path with the most ways to exist. Now picture a black hole. To the outside world, a black hole appears simple. A sphere of darkness defined by only three visible properties: mass, spin, and electric charge. Everything else about the matter that fell in is hidden. Yet the information is not lost. The event horizon stores it. The horizon becomes a library of information written in a language we do not yet speak. The amount of information the horizon can store is proportional to its surface area. When matter falls in, the horizon grows. When information accumulates, the entropy increases. But entropy cannot increase forever. Eventually, the horizon reaches a limit. It becomes saturated. It can store no further information because the surface area cannot expand without limit. This limit is more than geometric. It is fundamental. It is the reason gravity cannot grow beyond the Planck force. When the information capacity of a region of space-time reaches its limit, gravity has reached its ceiling. In that moment, the universe reveals its deeper structure. Space does not stretch further. Time does not slow further. curvature does not sharpen further. Instead, the relationship between information and geometry changes. The system seeks a new configuration that can accommodate the information without violating the law of entropy. Collapse ends not because gravity is opposed by pressure, but because no further arrangements exist within the current geometry. Collapse ends because the information ledger is full. This insight reframes everything. Gravity does not tell matter how to move. Information tells geometry how to bend. Matter follows geometry, as geometry rewrites itself to maintain information equilibrium. What we call motion is simply matter responding to incremental changes in the bookkeeping of reality. Consider two bodies drifting in space. They gradually move toward each other because that arrangement allows more microscopic information patterns. The attraction we attribute to gravity is simply the universe exploring the most probable configuration. The falling of an apple becomes not a pull, but an increase in entropy. The orbital motion of planets becomes not a balance of forces, but the natural shape of maximum information preservation. These ideas are not loose speculation. They are anchored in the holographic principle and in the mathematical relationship between entropy and surface area discovered by Hawking and Bekenstein. They are enforced by Jacobson, showing that Einstein equations arise from thermodynamics. They are extended by Verland, showing that gravity can be derived from information entropy. They are supported by ADS-CFT, which shows that a universe with gravity is equivalent to a universe without gravity living on its boundary. Every result whispers the same conclusion. Gravity emerges. This realization changes how we interpret black holes. A black hole is not a destructive pit. It is an engine that converts matter into information. The collapse of matter is a transition from one informational state to another. The event horizon is the interface where information is reorganized into geometric form. What lies inside is not emptiness. It is unstructured information that cannot yet express itself. When the horizon shrinks through Hawking radiation, information begins to leak back into the universe. Particle by particle, the horizon evaporates. The black hole that once only consumed now releases. The information is not destroyed, it is translated. The universe refuses to lose information because information is the foundation from which space itself arises. If gravity is emergent, then space-time is not fixed. It adapts to information. The universe is not a stage where matter performs. The universe is a conversation where information speaks geometry and geometry replies with gravity. At the deepest level, every event in the cosmos becomes a transaction of information. The collapse of a star, the orbit of a planet, the bending of light near a massive object, all of it is information exploring new configurations. The universe is not a thing, it is a process. And if gravity emerges from information, then when information reaches saturation, gravity stops being meaningful. The ceiling of gravity is not a wall, it is a threshold. Beyond that threshold, the rules change. Quantum gravity does not take over because gravity has failed. Quantum gravity takes over because gravity has completed its role. It has expressed all the information it can in geometric form. Beyond that point, geometry must reorder itself and create a new domain to store what cannot fit within the old one. When collapse reaches the ceiling of gravity, the universe transitions from geometry to information. The interior of a black hole becomes a birthplace for new spacetime, a Planck star, a wormhole, a separate region of geometry. The exact result depends on the deeper rules of information. Perhaps every black hole is a seed. Perhaps every seed grows into a universe. If so, then our universe is a descendant. We exist because information demanded more space than could be stored in the collapsing interior of a previous universe. Our cosmos may have begun not with a singularity, but with a limit. Gravity reaches its ceiling. information demands space. Space unfolds. The rules change. At first, it seems impossible to imagine a universe where gravity has a maximum strength. Gravity is the silent architect of the cosmos. It shapes the world without ever announcing itself. We feel it in the weight of our bodies and in the way a stone falls. We see it in the arcs of the planets and the spirals of galaxies. We depend on the idea that gravity will always respond to mass and energy, no matter how extreme the conditions become. But after exploring the deepest regions of theory, we begin to see a universe far stranger and far more elegant than the one our senses reveal. If gravity emerges from information, if curvature forms because the universe configures itself into patterns that maximize entropy, then gravity is not a fundamental law. It is a behavior, and behaviors change. When information saturates the geometry that stores it, gravity reaches its ceiling. Inside a star, gravity organizes matter into a sphere. Inside a neutron star, gravity compresses matter into degenerate neutrons. Inside a black hole, gravity compresses space itself. But at the limit, where no more information can be stored, gravity completes its function. It has organized the information as far as geometry allows. The universe moves to another rule. It is tempting to imagine that the story ends at that moment. Collapse stops. Information sits frozen. The black hole simply waits. But the universe is restless. Information does not remain static. Energy does not embrace stillness. When gravity saturates, reality finds a different path. In a universe without unlimited gravity, black holes are not tombs. They are gateways. They are the points where the rules of classical geometry surrender to quantum structure. When gravity reaches its limit, two remarkable consequences follow. The interior of a black hole cannot collapse into a singularity, and the early universe cannot begin from one. If singularities are impossible, then the beginning of our universe cannot be an infinite point. Instead, it must be a region of maximum density, where gravity reached its ceiling and space-time rebounded. The Big Bang becomes the outward expression of information unfolding after reaching its saturation. Our cosmos expands because expansion is the release of compressed information. Space stretches to accommodate a growing ledger. A universe without unlimited gravity rewrites the story of beginnings. We do not emerge from nothing. We emerge from transformation. A previous domain of space-time reached the maximum allowed curvature and gave birth to ours. In such a universe, black holes become cosmic mirrors. Each one contains the same physics that existed at the birth of our cosmos. Deep inside their darkness, collapse races towards saturation. The horizon hides the ultimate transition, but the process is the same. Information compresses until geometry can no longer express it. Then, geometry changes. If quantum gravity takes the form predicted by loop quantum gravity, the collapse rebounds into a Planck star. Inside the Planck star, space-time expands while the outside universe sees nothing happen. When the event horizon shrinks enough, the interior is revealed with a burst of released information. Black holes become temporary vaults of matter, waiting to re-enter the universe. If quantum gravity takes the form predicted by brain-world models, gravity slips into extra dimensions. The collapse does not rebound. It becomes invisible to our universe. The black hole is a drain where gravity leaves our geometric domain. The interior continues somewhere else. If quantum gravity takes the form predicted by the holographic principal, collapse becomes a reorganization of information on the horizon. Gravity is not acting. Information is reshaping geometry. The black hole evaporates gradually and returns everything it consumed encoded in radiation. 3 different interpretations. One unifying principle. Gravity serves information, not the other way around. In a universe where gravity has no infinite strength, every collapse has an outcome. Every black hole has a path. Every beginning has a cause. We can now imagine the universe not as a static space that holds matter, but as a dynamic conversation. Gravity is the voice that geometry uses to negotiate the placement of information. When the conversation reaches a point where no more can be said, gravity falls silent and new rules begin to speak. Imagine a future when humanity learns to read the language of information in space-time. We might learn that black holes are messages from earlier epochs of the universe. We might find that the seed of our cosmos lies inside a region where gravity reached its ceiling. We might discover that the universe itself is not a singular event, but an infinite chain of transitions, collapse, saturation, release. The most astonishing conclusion is not that gravity ends, but that it becomes something else. A universe without unlimited gravity is not missing gravity. It is abundant in possibility. When we finally confront the limit of gravity, we discover that the universe is not defined by force. It is defined by change. Gravity seems infinite only because we see its shadow. But every shadow has a source, and every limit reveals a boundary. The universe is not what pulls us downward. The universe is what lifts our understanding outward.